Hello, Maria, muted.
So hydrogen can be said to be is the first element. Hydrogen has 1 electron in the electron shell and 1 proton in the nucleus. Helium has 2 electrons in the electron shell and also 2 protons in the nucleus. So helium can be said to be made from hydrogen, in quotes, by adding an electron to the electron shell of hydrogen and adding a proton to the nucleus of hydrogen. Similarly, lithium has 3 protons, 3 electrons. That is adding an electron to helium and also adding a proton to the nucleus of helium. So in the periodic table, we are concerned basically with the number of protons. The number of neutrons is not involved in the construction of the periodic table. Now, based on the way the periodic table is constructed, it has been observed that there is a regular occurrence of similar properties at regular intervals. So at regular intervals, we see that some properties will occur. For instance, when we start with lithium, lithium has 3 electrons, it has 3 protons, it has 1 electron in its valence shell, in its outer shell, yes, valence shell. And also for lithium, the properties of lithium are similar to the properties of all elements that except hydrogen that have 1 electron in the valence shell. So that is what we mean by the occurrence of properties at regular intervals. So for instance, in the second period, when we go from lithium to neon, by the time we get to sodium, sodium also has 1 electron in its valence shell. The properties of sodium are similar to the properties of lithium, and that is what occurs. So every element that has 1 electron in its valence shell, and the valence shell is an s orbital, that electron, with all those elements, will have a similar property. This occurrence of similar properties is known as periodicity. So when we talk about the periodicity of physical properties, we are looking at the reoccurrence of similar physical properties at regular intervals based on the atomic number. Also, we have what we call the periodic law. The periodic law is sort of governs the properties of the elements in the periodic table. And the periodic law, the modern periodic law, which is what is current now, says that the properties of elements are a periodic function of their atomic numbers. And this draws from the initial statement I made that the occurrence of similar properties occurs at regular intervals based on the atomic number. So the periodic law tells us that the properties of elements are a periodic function of their atomic numbers. So when you look at the atomic number, you can use that to predict what you have for the properties. Please remember that in this case, we are looking at the atoms, the elements themselves, and not the ions. Now, this slide represents a periodic table. We have the first element, which is helium, and currently now the last element that is discovered is element 118. That is ogium. So we have the upper properties. We have the S hydrogen, I said, has 1 electron. Next to hydrogen is helium with 2 protons, 2 electrons. After that, we now go to lithium. We have beryllium, 4, and it goes like that until we get to element 118. We can now look at in the periodic table, we have 7 horizontal rows. So we have 7 horizontal rows, and each row is said to be is called a period. The first row, which is the first period, has only 2 elements, hydrogen and helium. The second row has 8 elements. It starts from lithium and it goes to neon. The third row has 8 elements. It starts from sodium and goes to argon. The fourth row has 18 elements from potassium to krypton. The fifth row from rubidium to xenon. And again, this also has 18 elements. When we get to the sixth row has 32 elements. The seventh row also has 32 elements. So these are the elements in the periodic table, a total as at now of 118. So each period starts with the filling of an s orbital and ends with the filling of a p orbital, except the first period. So only period 1 has the s orbital only being filled. But from period 2 to period 7, you start by filling an s orbital and you end by filling a p orbital. Now we have the vertical columns in the periodic table. These vertical columns are called groups. So we have the vertical columns, and the vertical columns are called groups. In the expanded periodic table, we have 32 vertical columns. These columns do not all start at the same time or the same place, and do not all contain the same number of of elements. So the columns differ both in number and also in both in number of elements and also in the nature of the elements that are there. So that is about the groups. The groups are actually more related. It is in a group that you have the recurrence of these periodic properties. So all elements generally in the same group have similar properties. They have similar properties once they are in the same group. Although the similarity in property is noticeable more for the elements that are in the S block and the elements that are in the P block. The elements in between the S block and the P block do not show that close relationship that we see in the S block or the P block. Now I've talked about the S block or the P block. What do we mean by S block? What do we mean by P block? Now the elements in the periodic table can also be classified based on the position of the last electron in the element. So in the atom of the element. So for instance, in hydrogen with 1 electron, that electron is in the 1s orbital. And so hydrogen can be said to be an s block orbital. Helium can also be said to be an s block orbital because the last electron in helium is also in an s orbital. But elements in period 1 are a bit anomalous, so we do not really treat them with the other elements in the periodic table. Rather, we look at them based on the properties that they show. For instance, helium with 2 electrons in the s orbital displays properties that are similar to the properties of elements with 6 electrons in the p orbital. That is why helium is placed under 18. Now we have the S block elements. These are 2 rows where you have 1 and 2. Elements under 1 and 2 are all S block because the last electron in that element, which we call the differentiating electron, is present in an S. Or the 2 columns under 1 and 2 are said to be S block. Now, after the S block, from 3 to 12, the elements from 3 to 12, which we start seeing at period 4, where we get to scandium, Sc. These elements are called the D block elements. And that again is because the last electron in these elements is present in a D orbital. Scandium has D1, and it goes through till we get to zinc that has D10. So all these elements within this family of scandium to zinc are said to be D block elements. And these D block elements are actually our transition elements. Currently now we have 4 rows of D block elements. 4 rows of D block elements. Then we have the P block. These are elements that start from column 13 to 18. And all these elements, except helium, have the last electron present in a p orbital. For instance, boron has p1. The configuration for boron, the outer configuration, is 2s2, 2p1. So the last electron in boron is in a p orbital. The last electron in carbon is a p orbital. The last electron in nitrogen is a p orbital, is in a p orbital. In oxygen is a p orbital. In fluorine is a p orbital, and in neon is also a p orbital. So elements that have their last electrons in the p orbital are said to be p block elements. Then we have this row of elements that are underneath, these 2 rows, which we have the F block. For these 2 rows of elements, the last electron in them is present in an F block element. And so they are called the F block elements. Ideally, these 2 rows of elements actually fit into this space between Ba, which is barium, and hafnium. So the 2 rows, La should be La to Lu, that is lanthanum to lithium, should be in between barium, Ba, and HF. And so that is their position in the periodic table. Similarly, the second row, which of the F block elements, will be between Ra, radium, and ruthenium. And that is between, so you have these elements in between, so in this vacant space, that is actually where it should be. But if we write a periodic table like that, which is the expanded form, it will be so wide. That is why the F block elements are now put underneath. So the F block elements, even though they are underneath, have their own space in this tabular arrangement. So we have the S block, we have the P block, we have the D block, and we have the F block. In this section of the course, we are going to look at the S block, we are going to look at the P block, and we are going to look at just the first row of the D block elements. Together, the S block elements and the P block elements are called representative elements. S block and P block are called representative elements. That is because when you know the chemistry of one element in any column in that group, in any group, any column in the S block or the P block, you have an understanding of the elements in that section. So that is why it is called representative. One element can represent all. That is, all in that column, not all of S and P. So what if I know the chemistry of sodium? I can now use the chemistry of sodium, that is Na, to explain the chemistry of lithium, Li, explain the chemistry of potassium, K, explain the chemistry of rubidium, Rb, explain the chemistry of cesium, CS, and explain the chemistry of francium, Fr. Similarly, for the P block, if I know the chemistry of oxygen, I can use it to explain the chemistry of sulfur, S. I can use it to explain the chemistry of selenium, Se. I can use it to explain the chemistry of tellurium, Te. I can use it to explain the chemistry of polonium, Po. That is why they are called representative elements. The S and the P block elements are related more in the group. That is, each group has a relationship, while the D block and the F block elements are related more horizontally. That is, from scandium to zinc, the relationship is closer than from yttrium to cadmium. So the D block and the F block elements are usually studied across the period, while the S block and the P block elements are studied down the group. Now, this morning we'll look at the periodic trends in some properties. I know that we have looked at some of these properties in FSC 112, but again, these are what we are going to use in this part of the course. So we'll just refresh our memory. So we'll just run through the properties and refresh our memories. So the major periodic physical properties that we are going to look at are the atomic radius, ionic radius, ionization energy, electron affinity, electronegativity, metallic character, and the melting and the boiling point. So we'll start with the atomic radius. What do we understand by the atomic radius? The atomic radius is actually half of the distance between the two nuclei of a homonuclear diatomic molecule. So I have a homonuclear diatomic molecule, which means a molecule that is composed of two identical atoms. So the half of that distance is what is called the atomic radius. So I look at these two, maybe look at bromine and bromine. These are two Br2. That is a molecule of bromine, and these are homonuclear species. So the distance between the nucleus of bromine 1 and the nucleus of bromine 2, that distance is twice the atomic radius, because the radius actually is the radius of one bromine atom. But usually the atoms do not occur just like that. The atom will usually occurs in a combined state. The most applicable state that is used is the covalent bond. But even if it is not covalent bond, the atoms will be related. If it's not by the covalent bond, it will be related by an internuclear bond, which is maybe the hydrogen bonding. It could be the van der Waals bonding. You can also have it having the metallic bonding. But half the distance between two nuclei of a homonuclear atom is the atomic radius. And why do we need the atom to be in the combined state? That is half. We are looking at half of the distance. Why don't we take an atom and say this is the radius? Remember that in our FSC 112, we were told that the atomic cloud extends. We have a period of high probability of finding the electron, but outside the nucleus, there's actually no region where you have a 0 probability of finding the electron. And so in order to contain the electron cloud and restrict the electron cloud, you look at a distance that is in half. You look at the atom in a state in which it is combined with another atom. So the second atom limits the extension of the electron cloud, and so allows us to be able to define the region of extent of the electron cloud. And so half of that is what, when it's in a combined situation, is what is called the atomic radius. Now, the atomic radius is influenced by 3 factors. The first factor is the energy level of the valence electron. The valence electron, remember I mentioned, is the last electron that is present in the last electron that is present in the last shell. the outermost shell. Now, the higher the energy level of the valence electron, the further the distance of the electron from the nucleus. And so the larger or the higher will be the value of the atomic radius. And the distance from the nucleus is actually placed in order of the energy level. For instance, if an electron is in the first energy level, it is closer to the nucleus than if it is in the second energy level. And if it is a second, it is closer than the third. The third is closer than the fourth. So the seventh energy level is where we have the greatest distance from the nucleus. Now we are looking at the seventh energy level, because you remember I mentioned that in the periodic table, as we have now, we have 7 horizontal rows. We have 7 periods. And each period represents of an energy level. So the energy level affects the valence electron. The higher the energy level, the further the distance from the nucleus, the larger the value of the atomic radius. Also, we have the nuclear charge. So we have the nuclear charge. The nuclear charge, loosely put, is the number of protons or the atomic number of the atom or the atom. Now, so the higher the nuclear charge, the closer the electrons are to the nucleus. So as remember, I said loosely put is the same thing as the atomic number. Now, the nuclear charge is positive, that is, the atomic number is positive, and the effect of the nucleus is that it pulls the negative electrons close to itself. So the higher the nuclear charge, or the higher the atomic number, the greater the strength in which the nucleus pulls the electrons to itself. So the higher the charge, that is the nuclear charge, the closer the electrons are to the nucleus. And the higher the atomic number, therefore, will be the smaller the size. Because the more it pulls the electrons to the nucleus, closer to the nucleus, the smaller will be the size of the atom. So the higher the atomic number, or the higher the nuclear charge, we expect that the size of the atom will reduce. Then the third factor is what is called the shielding or the screening effect by inner electrons. Now, this is the effect of inner electrons on the outer electrons. For instance, when you have inner electrons, the electrons that are present in an atom, actually, because they are more than one, will undergo inter-electronic repulsion, because they are same charge that are placed together, maybe in a confined area. And we know that unlike charges attract, like charges repel one another. So the electrons that are present in the atom actually repel one another. And the effect of the screening effect is that these electrons that are present in the atom actually serve to increase the size of the radius of the atom. So the shielding effect increases the size of the atom because it shields the outer electron from some of the effect of the nucleus, so that outer electron, the outermost electron, will not feel the effect of the nucleus as it ought to. And so the pull of the nucleus for the outermost electron will be reduced to what we expect. Remember, we expect that with the increased size of the nucleus or charge on the nucleus, the atom will be pulled to the nucleus more, and so there will be a smaller size. The higher the energy level in which we find the valence electron, we expect that the larger the size. And then with the shielding effect serves to also increase the size. So in the atomic radius, we have two factors that are opposing: factors that increase the size and also factors that decrease the size. So if the size is to be increased, it means that factor 1 and 3 That is, energy level and shielding effect or screening effect are more dominant. And if it is to be smaller, it means that the nuclear charge is the more dominant factor. So the factors are opposing. We have the factors opposing one another. Now the group trend across down the group. Down the group, as we go down the group, we find out that each atom, is in a higher energy level. For instance, in group 1, we have hydrogen. Hydrogen has hydrogen. Hydrogen has electron is present in the 1s orbital. Lithium electron is present in the 2s orbital. Sodium electron is present in the 3s orbital. Then we have potassium is present in the 4s orbital. We have rubidium is present in the 5s orbital. So as we go down the group, the energy level where we find the outermost electron or the valence electron is higher. And remember, I said the higher the energy level, the further the distance of that orbital to the nucleus, and so the larger the size of the atom. And so in this case, as we go down the group, there is an increase in size. There is an increase in size of the atom. And this is because as we go down the group, the the energy level where you find the valence electron increases. And also with that, you have an increase in the shielding effect. For instance, between the nucleus and hydrogen, there is no orbital. Nucleus in hydrogen, the 1s electron is the closest to the nucleus. When we get to the lithium, the 2s electron has a shield of the 1s orbital between the 2s valence orbital and the nucleus. So we have a shielding effect, a screen between the lithium valence electron and the nucleus. By the time we get to sodium, we have two screens. The 1s orbital is a screen, the 2s orbital is a screen, and then the valence electron is in the 3s orbital. And so we have two screens. By the time we get to rubidium now, which is 5s, we have 4 screens. Screen 1, screen 2, screen 3, and screen 4. Remember, the screening effect, like the position of the valence electron, both also serve to increase the size of the atom. So as you go down the group, there is an increase in size of the atom. The atomic radius increases. Then across the period, when we go across the period, in the period, the electrons are present in the same energy level. The valence electrons are present in the same energy level. The elements below represent the elements of the third period. They represent the elements of the third period: sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. All these elements are present, have their valence electrons in the third energy level. Although in sodium, it is in the 3s orbital, in aluminum to argon, the valence electrons are in the last electrons are in the 3p orbital, but all of them are in the third period. So within a period, the valence electrons are in the same energy level. And also as we go within the period, the valence electrons' positions seem to be constant. The nuclear charge increases because in sodium is atomic number 11, magnesium is atomic number 12, aluminum 13, silicon 14, phosphorus 15, sulfur 16, chlorine 17, and argon 18. So the atomic number increases as we go across the period. Now with the increase in atomic number and the same size, that is the distance between the nucleus and the valence orbital within each period is almost the same. That is, the energy level is the same. The only difference is that which orbital is filled within that energy level. So in that case, the nuclear charge, the increase in nuclear charge is the dominant factor. And that implies that as we go across the period, there is a reduction in size. The nucleus pulls the valence electrons or closer to itself, and so the radius gets smaller. So across the period, there is a reduction in this atomic radius. So size reduces across the period and size increases down the group. So we look at this period again, the same thing here. As we look at sodium to chlorine, you see that there is that decrease. The decrease occurs as we go across the period. So, and that is because you have the electrons, all the electrons present in the same energy level, and the nuclear charge increasing. So generally elements to the left of the periodic table are larger than the elements to the right of the periodic table. So each element in the period feels a greater positive charge, and that is because the electrons are pulling the element, the nucleus is pulling the electrons that are present in the valence shell more. That when you form ions from any species, it is the electrons that are either changed. Electrons are either added or electrons are removed. So we have two types of ions. Generally, we have the positive ion and we have the negative ion. The positive ion, which we call the cations, are obtained by the loss of electron from an atom, while the negative ions are obtained by the addition of electrons to an atom. Now, in the case of the positive ions, the cations, because you lose the electrons, for instance, in sodium, the sodium atom has the configuration 281. You have one electron in your valence orbital. The sodium ion Na+ is formed by the loss of that valence electron to give us 28, a configuration of 28. So you see that in the sodium ion, the valence electron, that is the 3s orbital that contains that one electron, is now empty. So the area of influence of the nucleus has been decreased by the loss of the valence electron. And so that nucleus will pull these electrons in the sodium ion, sodium plus cation, stronger than if you pull the electrons in the sodium atom. The nucleus is still 11 protons. So in the sodium atom, that nucleus will extend to the 3s orbital where you have the last electron. But in the sodium ion, the pull of the nucleus will only extend to the 2s orbital where you have 8 electrons. So the distance where you want the nucleus to act is smaller. And so the pull of the nucleus will be stronger. Now, so that is why the positive ions are smaller than the atoms that they come from. Now, for isoelectronic species, that is species that have the same number of electrons, the higher the charge on the nucleus of the cation, the smaller the size. For instance, sodium, magnesium, aluminium are all in the same period. In sodium, we have one valence electron. In magnesium, we have 2 valence electrons. In aluminium, we have 3 valence electrons. Now, in this case, when sodium loses its valence electron, you have the range ending at 2s, the range of the nucleus ending at 2p. When magnesium loses its 2 valence electrons, the region of activity or the pull of the electron also ends at, the pull of the nucleus also ends at 2p. In the case of aluminium, when aluminium loses its electrons, the pull of the nucleus also ends at 2p. But for these three species, sodium has a nuclear charge of 11, magnesium has a nuclear charge of 12, aluminum has a nuclear charge of 13. So we see that the nuclear charge is increasing. And so the nucleus with the charge of +3 will have a greater pull than the nucleus nucleus in aluminum will pull the electrons closer than the nucleus in sodium, because the nuclear charge in aluminum is higher than the nuclear charge in sodium, and the range in which we want it to act is still the same. We still want it to act over the same area, but we have increased the strength. Just as I usually say, that look at your nucleus as a magnet and look at your electrons as pins around the magnet. These pins are placed at different positions around the magnet. So in this case, for sodium, magnesium, and aluminum, the pins are in the same position, but the strength of the magnet is increased. With the increased strength of the magnet, that magnet we expect to pull the electrons or pins closer to itself with the increased strength. That is similar to what is happening. So as we go across the period, the size of the cation decreases as we go across the period. So the higher the charge, the smaller the size of the cation. Now the anion, which is a negative charge. The negative charge ions are bigger than the atoms in which they come from. That is because in the formation of a negative charge, we are adding electrons to the electronic shell. So in case of chlorine is present in group 17, and chlorine has 7 valence electrons around it. The electrons in the s orbital and the electrons in the p orbital. Now, when we now want to form the chloride ion, we add an electron to the chlorine atom. So we now form the chloride ion by adding an electron. As we add the electron, remember the electron we are adding and the electrons that are present in the valence shell of chlorine all have the same charge. And so there will be an inter-electronic repulsion. The electrons present in the valence shell of chlorine and any other atom of interest will sort of resist the addition of a new electron. And so there's what we call the inter-electronic repulsion. As a result of this, the inter-electronic repulsion, there is an increase in the size because the atoms now, the electrons now, will now position themselves at a distance that is not too close to its neighbors. When they repel themselves, they now have an equilibrium distance that is no longer as close as it was before. And as a result of that, the size of the anion is larger than the size of the atom from which it is made. Now, as you add more electrons to the electron shell, the repulsion increases. So the more the charge or the higher the charge of your anion, the larger the size of the anion. So for the anion, if you look at the anions, which are mainly formed from group 15 to 17, group 15, 16, and 17 elements are the ones whose atoms readily form the anion. The ion of group 15 needs 3 positive charge to have the noble gas structure. The ion of group 16 needs 2 electrons to have the noble gas structure. And the ion of group 17 needs just 1 electron to have the noble gas structure. So as you go across, you're adding less and less electrons, 3, 2, 1. And so the size of the anion decreases as you go across the period. The phosphorus group 15 will have the largest size, while group 17 will have the smaller size. But generally, the higher the charge on the anion, the larger the size. Please note that these are all for isoelectronic species. That is, ions that have the same electron configuration. Both phosphorus 3-, sulfur 2-, and chlorine-, all of them have 18 electrons, or all of them have 8 electrons in their valence shell. And so we are looking at isoelectronic species, 8 electrons, and the total number of electrons in those ions are 18 each. So please don't compare ions that have different electron counts. Don't compare ions that have different electron counts. Then the second factor is the ionization energy. Ionization energy is defined as the energy required to remove the most loosely bound electron from an isolated gaseous atom to form a positive gaseous ion, or to form a cation. Now, this definition actually is for the first ionization energy. And this is represented by this expression. You have X in gaseous X. X is my atom, my ion, my element of interest, my atom of interest. And it loses an electron to give me X plus E, a gaseous electron, a gaseous ion plus the electron. And so that is the first ionization energy. We are going from the atom to the ion. Now, apart from the first ionization energy, we have other ionization energies. We have the second ionization energy, the third ionization energy, we can have the fourth ionization energy. And in each case, we are removing 1 electron each. For the second ionization energy, we are going from the univalent positive ion plus X plus to X2 plus. So we are going from an ion to an ion of a higher charge. And so that will be the second ionization energy. The only one that goes from atom to ion is the first ionization energy. Now, the third ionization energy, you are going from X2 plus to X3 plus, and that gives us the third ionization energy. Now, so the one that we are looking at, the periodicity, is the first ionization energy. So generally, the ionization energy will increase as we go across. Why I say that is because, first of all, you are going from an atom charge 0 to plus, but by the time you now go from a charged species to another charged species, the ionization energy value generally increases. It is not in all cases, but sometimes you can have a reduction. But generally, you note that ionization energy increases as it goes from first to second to third and to fourth. But the one we are concerned with the periodic trend, is the first ionization energy. Now, the factors that affect the ionization energy, the nuclear charge, the shielding effect, the radius, that is the size, and the sublevel, or the sublevel in which you find the electron. Now, the larger the nuclear charge, the greater the ionization energy. Because the larger the nuclear charge, the smaller the atom, generally, the more difficult it will be to remove an electron. Also, the shielding effect, the greater the shielding effect, the less the ionization energy, because with the shielding effect, the size of the atom is increased, and so it is easier to pluck away an electron than from a longer distance from the nucleus. Then the radius. The radius, also, the smaller the radius, the higher the ionization energy. So ionization energy and atomic radius are inversely proportional. And then the sublevel. The sublevel, it tells us the particular orbital in which the electron is. Generally, when you have a filled or a half-filled sublevel, these ones have an additional stability conferred upon them. So when you have a filled or half-filled sublevel, then it is more difficult to remove the electron. So for instance, when I have a filled s orbital, S is a sublevel, P is a sublevel, a filled s orbital, to remove electron will be more difficult because it is already filled. And also a half-filled p orbital, to remove electron will be more difficult because the electrons are all filled in the same extent. So the filled or half-filled sublevel or filled or half-filled orbital has an additional stability, which makes removal of electrons more difficult. Now, the group trends. For the first ionization energy, we said that we are looking at the first ionization energy. As we go down the group, the first ionization energy decreases. And that is because the size of the atom increases. So as the size of the atom increases, the ionization energy decreases. Always remember, ionization energy and atomic radius are inversely proportional. And also remember down the group, shielding effect increases. Now the periodic trend, as we go across the period, the elements are in the same energy level. So we expect that as we go across, the size we know decreases. And so we expect the anion energy to increase as we go across the period. So generally, as we go across the period, there is an increase in ionization energy because the nuclear charge increases. So generally, nuclear ionization energy increases from left to right across the periodic table. However, there are exceptions. And these exceptions occur when we have the field sub-level or the field orbital or the half-field orbital. Now we have a field orbital at group 2, where we have the field s orbital, S2. All elements in group 2 have a configuration of, outer configuration of S2. And also when we have group 5 or group under group 15, when we have 5 electrons, when we have a half-field p orbital. The half-field p orbital also has a stability conferred upon it because each p orbital, based on Horn's rule, have 1 electron each. And so to remove an electron from the half-field orbital is reluctant. The atom is reluctant to lose an electron from the half-field orbital. So we have the exceptions at field orbital, field s orbital, and half-field p orbital. And this makes them have a higher ionization energy than expected. So let's look at this trend. These are the s and p block elements. Now we have this is S1, lithium is 1, group 1. This is group 2, beryllium, magnesium, calcium, and strontium are in group 2. And all these have a field s orbital, S2 is the valence configuration. So these have a field stability conferred upon them. And this is compared to the next one has the next electron in the p orbital. So while beryllium, magnesium, calcium, and strontium reluctantly will lose its electrons, which gives it its quite high ionization energy, the elements boron, aluminium, gallium, and indium will readily lose the 1p electron to give us the configuration of a field orbital. So we see that between beryllium or group 3, group 2, and group 13, we have that decrease. And also when we get to group 15, this nitrogen family, in the nitrogen family, the p orbitals are all half-filled, and oxygen that has 4 electrons in the p orbital, we also notice the decrease. And that is because the nitrogen family, which we have, has a half-filled stability and half-filled shell stability, while so your oxygen family will readily lose the p4 electron to get a p3 configuration. Then we look at the electron affinity. Electron affinity is defined as a change in energy when an electron is added to a gaseous neutral atom to form a gaseous anion. So we can say that the electron affinity is like the inverse of ionization energy. While ionization energy, you are removing electron to form a negative charge, a positive charge. In ionization energy, you are removing electron, you are adding electron, to form a negatively charged ion. And in both cases, you are removing them from a gaseous species. So again, I have my X as my atom, and X plus E will give me X minus. So that is my first ionization energy. And again, the trend we are looking at is for the first ionization energy. Like ionization energy, electron affinity. The trend we are looking at here is also for the first electron affinity, going from the atom to the anion. Then the second one is going from X minus to X2 minus. So you are removing, remember, you are always removing an electron at a time for you to have ionization energy, or you are removing or adding an electron, removing an electron at a time, yes, to have ionization energy. You are adding one electron at a time to have the electron affinity. You do not add 2 electrons together. You do not remove 2 electrons together. You are doing it. It is occurring in a stepwise manner. So that is addition of electron to form a negative ion. Generally, ion energy is expected to be exothermic, but for the metals, the S block element, first ion energy is not exothermic. So generally, a more negative electron affinity corresponds to a greater attraction of an electron in the atom. Now, electron affinity becomes less negative as we go down the group. So electron affinity becomes less negative as we go down the group. So less energy is released. Also, yes, is released when you have the formation of the ion as we go down the group, while it becomes more negative as you go across the period. Now, generally, I said it's exothermic because energy is given off. But for the metals, the addition of the electron to the valence shell is not a favored process, because all you are doing is making it, in quotes, generally more unstable. So for the metals, electron affinity is endothermic. So in this case, for lithium, in the sodium family, lithium is positive, sodium is positive, potassium is positive, rubidium is positive. So for the metals, especially group 1, electron affinity is endothermic. And that is because it is not a favored process. The metal will prefer to lose the electron to give you a stable configuration, which is the noble gas configuration. Remember that when any atom reacts, the tendency to react is for it to get a noble gas configuration. When you add electron to a metal or the first row to S block elements, then you are making it farther away from the noble gas configuration, which is not a stable configuration. So that is why you have the positive value, shows that it is not favored. But for the group 17 elements, electron affinity is negative. It is a very favored process. But whether it is group 1 or it is group 7, whatever it is, electron affinity reduces as you go down the group. It decreases as you go down the group, and it increases as you go across the period. Please note, when I say it increases as you go across the period, more energy is given off. It becomes more negative. More energy is given off as you go across the period. That is what we mean by increases. And when you go down the group, less energy is given off or less energy is required. That is when you say that it decreases across the period. So that is that for the electron affinity. Now we also look at the electronegativity. Electronegativity is the ability of the atom to add and to attract the electrons of a covalent bond to itself. Now, in a normal covalent bond, the two species share the electrons donated by each one, and the electrons donated are actually central between the two of them. No atom has greater possession of the electrons than the other one. But that is only true when the two species involved in the covalent bond are identical. If they are not identical, then it is not true. One of the atoms will have a greater pool of the electrons than the other one. The one that has a greater pool is the more electronegative atom. So when you are talking about electronegativity, please note, you are looking at attraction. It is not an energy term. Attraction of electrons in a covalent bond. And when that occurs, the one that has a greater electronegativity acquires a partial negative charge, while the one that has a lower electronegativity acquires a partial positive charge. Generally, metals have a low tendency to attract electrons and also a high tendency to release electrons. So if you have a metallic species present in a covalent bond, the metal will always have the partial positive charge. And when you have the non-metal will have the partial negative charge because it has a higher tendency to attract electrons. Remember, for the metals will lose electron to acquire the noble gas configuration, which is the desired configuration, while the non-metal will add on electron to acquire the noble gas configuration. And that is what guides it even in the electronegativity. So generally, as you go across a period, there is an increase in electronegativity. The most electronegative element in the periodic table is fluorine. while the least electronegative element in the periodic table is francium. Although francium is, because francium is radioactive, they usually put it as cesium because cesium is stable. So we have the most electronegative element being in group 17 and the least electronegative element being in group 1. The last element in group 1, least electronegative. The first element in group 17, the most electronegative. Sometimes they use the term electropositivity. Electropositivity, even though it doesn't have a real definition, it is just using it as an opposite of electronegativity. So we normally say that metals are generally electropositive, while non-metals are electronegative. But the one that has a trend that has been studied very well is the electronegativity. So we talk about electronegativity, ability to pull electrons to itself. And group terms, I've mentioned the group terms. So electronegativity decreases as you go down the group, and it increases as you go across the period. Then we look at the metallic structure. The metallic structure, the metallic character gives us an extent of the reactivity of a metal. Generally, a metal readily loses electron. A metal readily undergoes an electrovalent bond. So in the metallic structure decreases across the period. You find the metals to the left of the periodic table, and you find the non-metals to the periodic table. And also, the metallic character increases down a group. So if we are the S block elements where you have the metals, the elements underneath, that is francium or cesium, strontium, are the most metallic elements because they will readily remove electrons from them. They readily lose their valence electrons compared to the elements that are higher up. So metallic character increases down the group and it decreases across the period. So you expect that francium is the most metallic in group 1, while barium is the most metallic in group 2. So with that, we conclude this. So the melting point and the boiling point, these ones have no trend, but generally metals have a high melting and boiling point because the nature of bonding in metals is a metallic bond, which is highly directional, and it's highly directional, while for non-metals have a covalent bond, and so the covalent bond is generally weaker than the metallic bond, and so non-metals have a low melting and boiling point, except carbon in diamond. Carbon diamond has the greatest melting point because it is composed of strong covalent bonds, which are both the intermolecular and the intramolecular bonds. So with that, we have looked at the periodic properties of the elements, and we'll continue next week, Monday, and looking at the periodicity in period 3 elements. So thank you and have a nice day.